what we were doing is the filtering in this set of slides. Okay. So we start with a simple mean filter or smoothing filter. We try to smooth the image. Okay, this was the first filter. Then we said, okay, smoothing can by using some other type of filter, which is a Gaussian filter. Okay, so we take the Gaussian one. Then we said, okay, this is good for some random noise, but not for one type of noises. So we move towards the mean, max, and median filters, which are good for the different type of noise. Okay, this was all about smoothing or reducing the noise. And then we move towards the sharpening. Sharpening, we said, because smoothing we are doing, or in other words, averaging. And the averaging is basically it's a integration. So opposite to that will be sharpening, which will be achieved by derivative or the difference. So now we can find the difference either by the backward filter, subtracting the pixel I want to the previous pixel, okay, or the next pixel, or it can be from the two sides, okay, which is called the central. This is one of the examples that we did already, okay. So if we take that one, the differences, we can see that the resultant gives us some sharp transitions where we have the edges. Okay, like this is the edge, yes, this is the edge, and these are the edges. So where these edges, the difference is prominent as compared to smooth. Okay, but however, the first derivative actually has a problem that if you have a slope like this one, it will not be zero, but some constant value. So that's why we moved it towards the second derivative, which is taking accounts into the neighboring pixels, and subtracting from the current one. Okay, so this is the second derivative. If you do a second derivative, give more edgy-like thing. Edges and reduction is much better as compared to first derivative. And you can see that if I compare the first derivative with the second derivative, it's enhancing the edges. As per first derivative, when the slope is constant or just linear, so at that point we don't need edge because there's no edge here. So for now, this was all in 1D. For 2D, we went to the Laplacian operator. We call it operator or filter. Okay, filter or operator, the same thing. Okay, and what are these? We call it. Okay, let's say we have an image. Inside image, the numbers we call it pixels. Inside these numbers, for the filter, we call it weights, or another name, coefficients. So when we say for the filter, we don't use the word pixel. We use the word coefficients or the weights. For the image, we use the word pixels. And the same second order derivative, if we do it in 2D, and what we do, we take along x-axis the second derivative and add it to this second derivative along the y-axis. We call this a Laplacian. If we do that, we just have along the x-axis the second derivative, then along y-axis the second derivative. If we add it, so we get something like this. So what we are doing, we are adding the and below on the x-axis, left and right, okay, along the y-axis, and then subtracting from the current position. So to do in filtering is the filter, up and down, add and subtract from this. So from the equation to the filter, okay. So you should know how to make equation from the filter or filter from the equation, okay. Any question? I think we did it, okay. Last time we did this thing. So okay, now the problem with this is that we are subtracting with -4. So we are actually giving a negative weightage to the pixel that we have now, the location that is of interest. Okay, so this will create the edges, but in a negative direction. Okay, so somebody said, no, okay, let's take a negative of it just to make another filter. Somebody else comes up and says, why not we are ignoring these 4 neighbors? Okay, so that's why we add these 4 neighbors. Again, the addition of the coefficient in the case of sharpening should be 0. So yeah, why it should be 0 now? My question. Yes. Previously we said that some of the coefficient should be 1, right, for the mean filter. And why was that? Even the 1 is the same. Yeah, 1, 1, 1, 1.
We want to be in the top.
So why we want it? Because we want the brightness level of the image itself to be in the same range. Let's say image is 0 to 255. Okay, so if I apply the filter, it should be in the same range. If it's not normalized, okay, then what will happen is that it will go below or above 0 to 255. Okay, so the 1, because I want the levels not to exceed 0 to 255 in the case of 0 to 255. Okay, this is for that one. Here, why we want 0? Here, the reason is different. Why we want 0? Because assume that you have a image, this portion, a constant intensity. So what we want, if you have a constant intensity at region 3 by 3, at that point it should be 0. So this is the reason for this. Okay, so the reason for that is different than this one. Because if I place this filter on an image, try to apply this filter on an image, the region where we have a constant intensity should give you 0 because there's no sharpness there, no edge. So when there's edge, it will non-zero. If there's no edge, it will be 0. So that's why I want to make it 0. That's why when I add 1, 1, 1, 1, I make it -8. Otherwise, it will be not. If I make it 4, let's say -4. So even with the constant intensity, this filter will not give you 0. This should give you 0 because this is a sharpening filter, right? So when there's a constant intensity, there's no sharpness, right? Yes.
But here there is a possibility to have overflow also.
Yes, here then you have to normalize the image later on. So first apply the filter, then normalize it. Okay, even you do it, you can do it before, like in the mean filter or the Gaussian filter, you can do it. Okay, but there's a chance, there's a possibility we are doing it all at once. But here, no, either I can make these coefficient equal to 0 or 1. So I already make it 0 because of the sharpness. Okay, fine. But alone applying this filter alone on the image will just give you the edges. But this is not what we want. What we want is to sharp the image. So once I apply this filter, I get some edges, and this is the same image with just increasing the brightness. And you can see that only the edges are highlighted. The smooth part is actually gone. However, how to make this image sharp? Because this image and this image, there's a huge difference. I just get the edges. So what I will do, I will add these two, and this is like outline of the image, and this is the image itself. When I combine this, add it, it will be just a sharpened image, right? Yes. However, we have to make sure which filter we apply. If we apply this filter, I'm giving negative weight to the current pixel. Therefore, I have to subtract from the original. If I'm doing this, I have to do opposite. Right? I have to add these two filters. So it will be like something like this. Okay, the original image plus the filtered image, which is the sharp edges. Okay, but however, what is C? C will be -1 in the case of this one. Okay, however, it should be +1 in case of this, but it can be even more than 1. Like in order to sharp it more, you can give more weight to the edges. Okay, so once we do this, you get these sharp images as compared to this. Okay, so either it should be minus or should be plus based on the center coefficient. If the center coefficient in the filter is less than 0, it is minus. If it is greater than, it should be plus. Okay? -4 or +4.
The same sign as the center.
Yes.
And all W's should equal to 0, right? The summation. Or
Yeah, summation
should be equal to 0.
for sharpening. Yes. Okay, so let's put the value of the gradient here. What was the gradient? It is the sum of the left, right, up, down, and -4. If I put the value, what I get, because now what I'm finding edges and then subtracting or adding to the image, right? So it's a two-step. So let's put the value of the gradient to make it just one step. Okay, if I just do this, how I can simplify it? This will be added to this, right? So it becomes +5. Okay, so if I do this, I get this filter. So if I apply this filter to image, it means that it will directly give me the sharp image instead of doing this. Okay,
The sum is 5, 1 here. Will you do the sum of the other? This filter?
no, because edge filter is this one. Now this is actually the image filtered image. You can call it filtered or sharpened image, but this is not directly. Okay, fine. So if I do this, you can see some sharpness here. If I just compare these two, you can see that how sharp it is. Okay, so we talk about the second derivative, and based on the second derivative, we have Laplacian, right? Laplacian filter. But we also have some filter based on the first derivative. Some scholars, they just propose first order derivative filter. So how will it look like? If I just take the first derivative along x and y axis, this is along the x axis of the image. So how to take the first derivative? It depends. Okay, either I have forward, backward, or central. Okay, and then take the along the y axis. So if I take these two gradients of the image, how to make one image? Because if I take this one, it will give me one image, right? Along x axis. The other one is along y axis. So what to do? So I can take the magnitude, the x square, I take this square and this square to get edges. Yes or no? Okay. Now, based on gx and gy, which is the gradient along x-axis and along y-axis, there are like around 3 filters. One is the simple one, which we already discussed. Like, for example, if I take, let's say, this is image, z5, okay? So I can subtract these two, which is the forward derivative, right? Okay, so I can subtract these two along x-axis and then these two along y-axis. So this is simple. We call it just simple filtering. Okay, and there are some other scholars like Roberts. He proposed another one. Why not, instead of doing just horizontal and vertical, why not we just go diagonal? So it will subtract this and then this. Okay, so z9 minus z5, this subtraction, and z8 minus z6. Okay, like this cross, this one and this one. Okay, so how to do that? If these two can be written in terms of the filter as this. Okay, if I apply this filter, I get the same this, right? I am subtracting z5 from z9, right? So this will be like this, and then this one will be like this, right? So these two, if I apply this filter first and then this filter second, will get gx and gy. And after that, I will take the magnitude to get the sharp image. Yes or no?
But okay, what is the intuition behind this diagram?
Because the edges may be inclined. Okay, but again, you see the specific type of kernels may be good for one image, might not good for another image. Okay, so that's why we have a lot of kernels. Not only this, still people are doing this side. Now you see, there's another scholar, Sobel, which proposed another thing. He says, okay, why not just to subtract above horizontal with horizontal, with the lower one, and vertical with verticals to get this pixel area. And if this subtract this, you get one gx, and then this subtract this, you get gy. And to get edges, okay, I have to take the magnitude. Now see, either you can take this magnitude, but this has square plus the square root, right? So sometimes computation wise, it's not that efficient. Some of the scholars, they approximate it with this one, taking this the absolute and adding that. Yes or no?
This is the sum experiment?
Yes, of course, the experiment. Plus, if you see if I just see this value together with this value, it will be very close because I'm taking the square then square root, right? So let's say if they are both equal. Okay, so a square might be cancelled with the square in some cases. Okay, so that's why we said approximately. Okay, the mathematical as well and experimentally definitely they prove it. So is this clear? Either now the first order derivative, either we can take diagonal, which is we call it Roberts, simple one, just taking the subtraction along the x-axis and y-axis, or this was horizontal wise or the vertical wise. So I have given some examples. This is the image, and these are the operators or the filters that you have to apply. So what you need to do, this is the image, apply this one, convolution. On this one, you get one image. Then apply this one, you get another one. And then pixel wise, you square both of them, add them, and take the square. You get the resultant. So here, I just showed this one. You can just take the absolute and add them, so it will be less. Okay.
Maybe for all the values of that.
Yes, term by term. Okay, this is what I'm saying. The actual operation is not difficult. You will be given this filter. How to apply it? Apply this filter on this using convolution. Apply this filter on this using convolution. You get two images. Square each pixel on these two, then add and square root. You get this one.
Why is X on the edges?
X means that I just zero pad it. Okay, then here I don't care. Okay, what is in that? Because this is nature. This is the sharpening image. If I take this one, 0 and then 6. So here it's a smooth image. It should be 0 all the way. But you see that there is some values. Why is the values there? Because of zero padding. And this is the problem with the zero padding. If I zero pad it, that from 0 to transition to the image, there will be some edge which should not be there.
So what happens to the black?
Yes.
So the black will be 0 on the left, and then
Yes.
back it will be 1
Yes.
because there's edges.
Okay. And similarly, if you want to apply the Robert for it, it's 2 by 2. It's not 3 by 3. 3 by 3, I know that I have to put zeros all over the image. But for 2 by 2, where I am applying, okay, where the value will be assigned. For 3 by 3, I know that it will be in the middle. 5 by 5, I know that it will be in the middle. For the even filters, you have to select this one.
The edge
Okay,
is the top here.
the first one. Okay, this one. I mean, if I apply, let's say here, so the value will come here. Similarly, this one, the first one. The first block will be the one. So if we have this, I don't need to pad it all equal, right? Okay, because I'm starting from here and I have this value, right? So only pad on this side and downside. Okay, so if I apply the Sobel operator, I get the edge. You see this one? I get the edge, very nice edge. Okay, then now we discuss sharpening filter, discuss second order, first order. There is another very interesting method of sharpening, and that is not directly a sharpening filter, but it is something to do with the blurring. Okay, for example, let's blur the original image. So what we did, we just smoothen the edges, right? So if I subtract that image from the original image, what I will get? Make sure I have the image. Okay, I have the image. I just blur that image. Okay, if I blur that image and subtract from the original image, what I will get? Get the edges. Yes. So if let's say this is a very good example. I have this 1D signal. So when I smooth it using Gaussian filter or maybe the other simple averaging filter, what I will get? Smooth edges here, like this one. If I subtract them, what I will get? Edges, right? And if I add these edges to the original one, I will get this. So what I did, I just highlighted the edges. So this is what I blurred the image. I blurred it. It's called it F dash. Then I subtract from the original image to get the edges, and then add to the whatever I get the original image to get the sharp. So you see here, if I apply the same, we call it unsharp mask. We are making the sharp, but using unsharp, right? Because we blur it first. Okay, so it's somehow making the sharpness, but using the blur. So that's why the name is also very interesting, unsharp mask.
This sharpening. I know we are unblurring and then sharpening.
It's a sharp, yes. Yeah, unsharp because we first unsharped it. That's why I call it. Okay, guys. So yeah, this is a very interesting, the same example, original image, and we blur it after blurring. Okay, original minus was a blur image to get the unsharp mask. That's why we call it unsharp mask, because we subtract them and then add to the original image to get the sharpening. So just try this example. So we finished the filtering in spatial-domain. The next step will be the frequency domain. And what we did two filters mainly. One was the smooth filter, and the other was the sharp filter. The smooth filter in frequency domain is what? Low pass filter, because we are just passing the low frequencies or we are smoothing the signal. The high pass filter is equivalent to the sharpening because we are identifying the edge. If I just want to make the low pass filter in the frequency domain, it will have a low pass frequency, and the frequencies below this band will be passed and other will be stopped. Yes or no? High pass filter, below this will be stopped and above this will be passed.
What does that mean?
Stop.
Zero.
Okay. Then we have band reject filter and then band pass filter opposite to each other. We have band stop, it means zero frequencies from here, then and it's okay. And these filters are somehow related. Let's say you have a low pass filter. If I subtract from one, I get a high pass filter. If I subtract a low pass filter from one, I get high pass filter. Similarly, the band reject filter is actually a low pass filter plus a high pass filter with two different frequencies. Then we have a band pass filter, which is 1 minus band reject filter. Why I'm doing this? Because although we did not discuss up till now these type of filters in detail, we will discuss in detail. But I know that you must have some background about the low pass, high pass. This is very basic, right? To give you understanding that how we can make the other filters from our knowledge that we applied now. Okay, so we had the low pass filter, a Gaussian filter, and the mean average filter was the low pass filter. So if I subtract here, I was subtracting 1 minus this. 1 in frequency domain is what? If you have a constant signal in a frequency domain, having all the frequencies, what will be it is in time domain? So 1 in frequency is basically impulse. So let's say I want to do the same thing here in time domain or in the spatial domain. I have a low pass filter. In order to have the high pass filter, I subtract low pass filter from impulse in 2D. I get high pass filter. For the band reject filter, I will have two low pass and high pass with different cut points or different frequencies. I get band reject, and band pass filter is the 1 minus band reject, which is in time domain or the spatial domain, it will be impulse minus this. Yes or no? Okay, this is very good example of band reject and band pass filter. You have this image. So let's say I apply a low pass filter. So which frequencies here you will see? Okay, where are the high frequency and where is the low frequency? If you see here, it's if you move like this way, you have low frequency and then becoming high frequencies, right? So if I apply a low pass filter, I will remove the middle. Low pass. Okay.
Leave the middle.
So leave the middle, and the other will be a blurry image. It depends on the filter type. Maybe this is not very good filter, so it's still there. You can see the smoothness. Okay, but you cannot see the smoothness inside because low pass. And then if I apply high pass filter, I will completely get rid of this. Only the edges will be prominent at the high part. Yes or no?
But what is the width of this filter that tell us this is high or low? For example, if this is usually in the middle, in these parameters, it is low as, but in these parameters, it is high.
Yes, it's a comparison. Okay, I'm just discussing the
There is something like width.
for the filter here. Definitely there will be something.
By looking to the image, how can you tell where is the high frequency?
If
By
you
blurring?
if you go like this, that it is low high, it is 0 and 1. Okay, so we have 0 1 0 1. So how much frequent it is going? Okay, 0 and high. If you see here, it's quickly moving from 0 and 1. However, if you go from here this direction, it's like less frequent, right?
Is it with the blurring or no? The repetition of
The repetition of the rings, in other words. Okay, the repetition of the rings. The distance is very
unit
far.
length? How many repetition in 1 unit length?
Yeah. Yes. Okay.
Has nothing to do with the blurring.
No. Okay, take from one point. You take any line from here, what you will see. If I go here, it is yes. It's like wider and smoother. This is high pass, this is low pass, this is high pass.
Above smoothing, not smoothing, right? And under with the smoothing, you have.
Under with smoothing, yes, smoothing will only have this area.
What is about this last one?
Last one is the same image, just to increase the brightness. Okay, and then this is what band pass. Then what is this? Band reject. Okay. Last is just enhancement of this. Just increase the brightness because it's dark. Okay. Okay. Now see, if I want to make a high pass filter from a low pass filter, I have a low pass filter and I have an image. Okay. So in order to make a high pass filter from the low pass filter, what I should do? Subtract the impulse from the high pass filter. What is the impulse in? The impulse here in 2D is just like impulse at 0 0 location. Make sure the 0 0 location for the filter is in the middle. Unlike the image, it's on the top left side. Yes or no?
Yes.
Okay, any question up till now? This is for you, just to practice. A high pass filtered image is equal to original image minus the low pass filtered image. Can you prove this? Okay, so just using the equations that we have, prove that the high pass filtered is equal to the original image minus the low pass filtered image. Okay, so now see, all these operators that we discussed, which includes some thresholding at the start. If you remember before the filtering, you have some gamma corrections, thresholdings, then we discussed the mean, max filters, and all these. Sometimes we don't just pick one of them. We can have series of these operations to get the final thing. Okay, what is meant by this? This is example. Okay, this is the original image, and we want to make it look good so that it should identify all the bones and all the structure very well for the doctors. Okay. Now, one way is just to make it sharp. I will apply the Laplacian filter and then add 2 to get it, but still it's not good. Okay, so we need to apply a series of all the operations that we discussed. Okay, so first we take the original image, apply the Laplacian, which we already discussed. This will give me the edges. Fine. Then adding the Laplacian with this one, give me this image. Then the Sobel operator to make the edges more prominent. Okay, if I apply the Sobel operator, first derivative, it will make the edges more prominent. Yes or no? Okay, I'm doing series of it. First pick these two, add these to get this, and then on this I'm applying this. So I'm just making some more operation, not just one operation. Okay, then I smoothen the Sobel operated image, this one. Okay, I smoothen it, and why I'm smoothing it? To make the dot mask. Okay, then I multiply with the Laplacian image to get the edges again, and then again add this one to the original image. Okay, after that, I finally apply the power law based intensity transformation to get this image. So if you compare this image with the original one, how much improvement I get? See the last one with this one. So this is a lot. So this is based on experience. I hit and try, apply this and that, and also based on experience, you say, okay, what I need more. Okay, let's apply the Sobel operator. Maybe it will improve. So based on when you are playing with the filters, you know which filter will fit best. Okay, so by this we just like finish the filtering in spatial domain. The next is now to apply the filtering in the frequency domain. Okay, like the high pass, low pass, the same filters. But before that, we have to understand what is frequency domain look like in 2D. Okay, and before that, to go to 2D, we have to understand 1D. So I recap 1D first, which I will try to do it quickly. Yeah, so we were like this here, transform domain. However, I just skip it because now the DL methods, deep learning or the neural networks or CNN methods are also very suitable to what we discussed, because we discussed convolution, we discussed the filtering. Neural networks are nothing but just a filtering operation. Yeah. Okay, you can consider this in this way. Maybe some of you might have some experience in dealing with the neural networks, but hopefully the way I will go or approach neural networks will be, I think, will be different. Okay, so one of the thing is just you can now see this is a very good example. Here, what we did, the last slide. If you see the last slide, in the last slide, what we did a series of operations to get the value. Now, let's say if I train a filter to input this thing and get this directly. Let's say you have a filter that input the original image with the person and output the clear one. So what will happen? This type of filtering, one of the best way is using neural networks. So what I can do is this, because this operation is very tedious, right? Very tiring. You have to apply so many operations. So what I do, first I will enhance some images, try to apply these operations in series or the way I want. And then I can train all these images I can train because I have the original image and the enhanced one. Okay. So I can just train it so that there is some filter with the weights and that can actually train to get the image I want. Yes or no? Yes. So what the neural network will be look like? One way is, let's say I have image and I multiply this with another image to get the image of my choice. So let's say you have an image 1, 2, 3, 4. I multiply the filter, which I don't know, to get something else. Let's say 101, 202, something like that, 5, 809, and so on and so forth. Okay, so what is this? This is the filter, but this is not exactly the convolution, right? I just point by point multiplying it to get the value. And from here, the concept of, we call it a simple neural network, or we can also call it fully connected, because everything is connected fully by element. Okay, so from here, the origin of the neural network starts. However, what is the problem? The problem is, if this image is 256 by 256, I need 256 by 256.
Which is going to take a long time.
Yes. Okay. However, it revives itself when with the origin of 1. So instead of multiplication, why not I do a convolution? The convolution that we talk about. Why not we do convolution? And when it becomes convolution, we get convolutional neural network, which was efficient because the size of this not necessarily to be equal to the image. So this was actually the major breakthrough that made the neural network again become alive. Because of this, we have, which we call it deep neural network. What is deep? If I had more layers, it will be very computationally expensive, right? So that's why we cannot, in the original neural network, the layers was like 1, 2, maybe not more than that. But when we become convolutional, we can have deep neural network, which we have like more than 2 and 3 layers. And we'll just talk about all this.
Okay, but now, how many images are these? Is it, I mean,
Now there's no clear answer. There is some steps to need to be followed. Okay, so
is it one enough?
one can be enough. You cannot train it like whole image. For the one image, you have to break down into a segment, small images, and then train neural network. It cannot be one. It can be one if you divide it into a segment. So in other words, it's
even
not.
though if you divide in the segment, that when you have this image different than the original one,
When you divide it, then it can be different. Make it a segment. Okay, should be like
Like different number of projects, like cannot have all these hundreds of images. And the scenarios just change the loading on the generator.
Yes.
That's the maximum. And sometimes when I load it, even the subsynchronous phenomena will not be there. So now,
in that case, since I need more than one, but you don't have, what I can do is to divide these images in small images and try to train them.
I have a question. Is there a possibility to apply this square method here to get this filter race?
You have to apply this.
With a lot of training? In one
If you least using, there are two types of least. One is the minimum mean square. If you're directly using a least square, no, you don't need it. Okay,
So
but
maybe-
yeah, but however, the problem, are you taking it in course? I think. Okay, so there's a this problem of inversion because you need to invert the matrix. Okay, so this is very, so in order not to do that, you have to make it iterative. Okay, iteratively. Recursive. So for the recursive, definitely then you need this.
But in only you can do it if it is not inversion, the vector itself, it is not the weights here, it is not invertible. So we do some trick to make it some inverter, right?
No,
To make the theta.
this is a vector, however, because it's a vector convolved with a matrix. So if you have a vector convolved with a matrix, you can write in a matrix multiplication by a matrix. So that's linear matrix. That's not a problem. But inversion itself is very expensive. Matrix inversion is very expensive.
But it's possible. Expensive, but it's possible.
Yes, possible. But if let's say you have five, you invert this, or maybe 512 by 5, or the image is 204, 1024 by 1024. It will be like, you can try it in a MATLAB, you will see.
Okay.
The issue of the size of the
Yes.
data that you use.
That's one. Otherwise, even the convolutional neural net, instead of the iterative, you can use just one step to get it, but it will be very expensive because you have very big matrix.